Hey everybody, welcome to Math with Ace. We are focusing on statistics and we are going to be dealing with hypothesis testing. We're going to do the whole thing all the way through where we are checking conditions, making sure we're ready to proceed. We're going to be running the numbers by hand, also using Stapplet to help us, and stating our null and alternative hypothesis, and then drawing a conclusion. I like to call this our four-step process where we state, plan, do, and conclude. Got that from some of my favorite textbook authors, and so I just like to keep that going. So the first thing that we do is we're going to state our null and our alternative hypotheses based on the question. So let's do a little analysis. Statistics students of a large college, that's important, large college, believe that the mean score of the first statistics test is a 65. A statistics instructor thinks that the mean score is higher than 65. And the instructor randomly samples 10 statistics students and obtains the following scores. They perform a hypothesis test using a 5% level of significance. The data are assumed to be from a normal distribution. Is there evidence to support the instructor's claim? Okay, a lot of stuff that we highlight. Some of them are related to conditions. Some of them are related to the actual null and alternative hypotheses. So the first thing we want to do is set up our null hypothesis and our alternative hypothesis. And we need to determine what this problem is about. Remember that the null is always a statement of equality. So we're going to determine what the problem is about, define the parameter and context, and then we're going to proceed with conditions. We were given an alpha equals 0.05 level of significance. We're going to jot that down. That is our baseline. We need our evidence to have a probability of less than 5% for it to be significant for us. This problem tells us the mean score, and we're given a list of numbers. Because this is numerical data, we are dealing with averages. This proportion is a mean, which we represent with mu. And we are told that we want to know if we're testing the instructor's claim, and the instructor claims that the mean score is higher than 65, and higher is represented with the greater than symbol. So since we're using 65 here, we are using 65 in the null hypothesis as well. And then we're also going to identify the parameter. So mu is the true population mean score on the first statistics test. Okay, now that we have set up our null and alternative hypotheses, we've identified our parameter, and we have written our level of significance, we're going to move on to our conditions. So we're going to plan by checking random, independent, and normal. It is not sufficient to write a check mark and just say yes. That does not show how you are checking conditions. In order to check conditions, you need to show what you are doing to verify these things. So in order to be random, it really needs to be told to us that this was a random sample. And in the second line, it does say the instructor randomly samples. So for random, we can say the sample was stated to be random. For independence, we are verifying that our sample size is small in relation to our population. So these students come from a large college. We sampled 10. So n equals 10, and if we multiply 10 by 10, because we're looking at 10%, that's 100. So we need to ask ourselves, is there more than 100 students at a large college? Absolutely. More specifically, we're talking about statistics students because it's a statistics class, but there are in a large college at least 100 statistics students as well. Now, for large counts or normals for averages, there's 3 ways you can meet it, and you only need one of the 3 to work. Your sample size needs to be at least 30 for the central limit theorem to apply. It is not. We would need to graph the data unless we're told that this is a normal distribution. And for the neat and tidy problem that we have, we are told that this is a normal distribution. So we can say we are told to assume the distribution is normal. So conditions are met, we can proceed. If conditions were not met, we would say conditions are not met, we're not going to proceed. So now we're going to run the numbers. And in order to do that, I need to know what the sample mean is. I need to know what the sample standard deviation is. I need to know what the sample size is. I need to calculate my test statistic, and I need to calculate my p-value. And I'm going to enter the information into Stapplet, our free applet resource. We're going to go into one quantitative variable, and this is first statistics test scores. And I'm using raw data because I have the actual scores. If you were to, you can use the mean and the standard deviation or the 5-number summary to help with this. We're going to use raw data. So we have 65, 65, 70, 67, 66, 63, 63, 68, 72, and 71. Now, beginning analysis towards the bottom, you can see that the sample size was 10, the average was 67, the standard deviation was 3.197. Our degrees of freedom is n-1, which is 9. And I'm actually going to calculate the t-score by hand. Remember that the t-score is the sample mean minus the hypothesized value divided by the standard deviation of the sample, which is divided by the square root of n. In order to do that, t is 67 minus, we hypothesized 65. All of that is over 3.197 divided by the square root of 10. I'm going to use my calculator. 67 minus 65 is 2. And then we're going to divide that by 3.197, which is also divided by the square root of 10. And we get 1.978. So what is the probability that t is greater than 1.978? That's our p-value that we're looking for. We can actually perform inference on Stapplet by selecting a one-sample t-test for mu, where we tell the hypothesized mean and a greater than. And we are given our t-value, which we had, our degrees of freedom, which we had, and the p-value, which is 0.0396. And now we draw our conclusion. So we look at our level of significance and we look at our p-value. And how does 0.0396 compare to 0.05? If you struggle with comparing decimals, you could move both decimals twice to the right, and you could look at 3.96 in comparison to 5. 3.96 is less than 5. And what that means is our p-value is less than 5. So 3.96% is less than 5%. This means that assuming that the test score was 65, only 3.96% of the time would we get the test statistic that we did, or the sample data that we did, or data more extreme purely by chance, assuming that the test score was 65. So this is saying it's really unlikely that the test score was 65. It's likely that we have evidence for the test score being higher than 65. So the way that we draw our conclusion is we say, since our p-value, and we list our p-value of 0.0396 is, and this is where we compare it to the level of significance. So it is less than our alpha equals 0.05 level of significance. P-value low, reject the HO. we reject the null. This means there is sufficient evidence for the claim, and we give it context. There is sufficient evidence that the true population mean test score, statistics test score, I want to say, is more than 65. Okay. In our next video, we're going to do a hypothesis test all the way through for proportion. So feel free to stick around.